Welcome to Math 201, Lesson 2.6 on differentiability. A function is said to be differentiable if its derivative, which you should remember the definition of derivative is f prime of x, is the limit as h goes to 0 of f of x plus h minus f of x all over h. So a function is said to be differentiable if this limit exists. So we've seen a few ways for a limit to fail to exist. You can have an asymptote, a hole, or a jump. And here are the basic ways a derivative can fail to exist. We could have a corner, okay? And remember, the derivative is the slope of the tangent line. And so at a sharp corner like this, it's impossible to decide how to draw the tangent line. Do you draw it like this? Do you draw it like this? Do you draw it straight across like this? So in the case of a sharp corner, when we say the slope of the tangent line or the derivative, it's impossible to know what that value should be. Now, a vertical tangent line is also a place where the derivative does not exist because the slope of a vertical line is undefined. Okay, so when you have a tangent line that's vertical, we say the derivative does not exist because the slope of the tangent line is an undefined quantity. And then finally, when you have a discontinuity, there are too many possible ways to draw the tangent line, right? Like, so if I draw a tangent line right here, it doesn't actually touch the graph because there's a hole at this one point where we want it to touch. And then if I decide to draw at the point itself, there's a million different ways that you could draw a tangent line there um, for a line that would go through that point and touch only once. And then this one doesn't work because it won't touch the graph at all. Okay, here, vertical tangent line undefined. So we say the derivative does not exist. And at a corner, there are too many ways that we could draw the tangent line. So we have to say that it doesn't exist because there is no one answer. Identify all points of non-differentiability for each of these functions. So any place where we have a discontinuity, we definitely don't have differentiability. So at every integer here, right, at 1 and 2 and 3, right, where we have these jump discontinuities, so we have non-differentiability. And then for the second graph, we have a vertical tangent line here at x equals 0. So this is not differentiable at x equals 0 because I have a vertical tangent line. And then for this last graph, this last function, I need to graph it. I didn't give you the graph. We're going to have to draw it ourselves. So it's f of x equals x for x is less than 3. So I'm just going to put a open circle there. And there's my line. And then 2x minus 3 for x is greater than or equal to 3. So if I put a 3 in there, I get 2 times 3 minus 3, which is 6 minus 3, which is 3. So that means I can now fill that circle in. Okay. And then another point on the graph would be, let's see, if I plug in a 4, I get 2 times 4 is 8, minus 3 is 5. So 4 or 5 is another point on this graph. And it looks like that. And I have a sharp corner at this point. So it is not differentiable at x equals 3. Here are some different ways that we can speak the language of differentiability. Um, differentiable at x equals 2 can be shortened to just differentiable at 2. Differentiable on the interval from 0 to 5 means that it's differentiable at every x value between 0 and 5, including the endpoints. And differentiable everywhere can be shortened to just differentiable. If you say a function is differentiable, what you mean is at every point on its domain, it is differentiable. So this is the first activity for lesson 2.6. Please pause the video, work through this activity on your own, and then come back and watch, um, and we can go over it together. So Mandy takes a walk. Mandy the ant is walking along the number line. You record her movement for 10 seconds from t equals 0 to t equals 10. Let y equals f of t be a differentiable function that gives her position on the number line at time t. For each question below, determine what each situation implies about f prime of t and f double prime of t. You may circle more than one word, and then sketch a function f that satisfies the stated requirements. Okay, from t going from 0 to 10, Mandy moves forward at a constant rate. So we have time in seconds, and then we're going to have distance um, from starting point on the y-axis. And if she's moving at a constant rate, we're going to say she starts at some starting point at time t equals 0, and she's just going to move at a constant rate. So her distance is going to just be increasing. Okay. So that means that f prime of t is both positive and constant. So if I'm looking at the slope of the tangent lines along this line, okay, I'm going to draw little tangent lines. They look like this. Okay. So those lines all have positive slope, and they are always the same value. Okay, so f prime of t is positive and constant. And f double prime of t, which tells us about the concavity of f, um, remember that if f double prime is positive, then f is concave up. And if f double prime is negative, then f is concave down. And this is my graph of f, right? We've just drawn f, which does not have any concavity. It's not up like a cup. It's not down like a frown. It's flat, okay? So that means that f double prime has to be 0. Okay, when there's no concavity, f double prime is 0. Okay, so now for all t in 0 to 10, Mandy moves forward and she is speeding up the whole time. So she starts at time 0, distance 0, and then she's speeding up. So that means that her velocity is increasing. Um, so we would say f prime, which represents velocity, is increasing. And remember that when a function is increasing, its derivative is positive. So f double prime is positive. And when f double prime is positive, that tells me that f is concave up. Okay, so if I draw a picture where Mandy is moving forward, her distance is increasing from the starting point and it's concave up. So f prime we know is positive because the graph is increasing, and increasing because the graph is concave up. And f double prime is positive. Okay, now for all time t in 0 to 10, Mandy moves forward. So her distance should be increasing. She's moving forwards, but she's slowing down the whole time. So remember, slowing down, that's her velocity. So f prime is decreasing. Okay. And we know that when the derivative is decreasing, or when a function is decreasing, its derivative is negative. So f double prime should be negative. And when a second derivative is negative, the function f is concave down. Okay, so I'm going to start Mandy at 0, 0. Let's label this distance. She's moving forward. She starts at time 0, distance 0. So her distance is increasing. It's getting bigger, but it should be concave down because she's slowing down. Okay, so f prime we know is positive because f is increasing. Um, and f prime is also decreasing. And then f double prime, because f is concave down, f double prime has to be negative. Okay, for t values between 0 and 5, Mandy moves forward while speeding up. And then from 5 to 10, she moves forward while slowing down. So if you go back to the previous two questions, we know what moving forward, speeding up looks like. That's concave up. That's increasing concave up. And then moving forward while slowing down, that is decreasing. Sorry, that's still increasing because you're moving forwards. So you're still increasing, but concave down. Okay, so I can draw it. put 5 in here. So start at 0, 0, and increasing concave up until 5. And then she continues moving forward. So we're still getting further and further away from the starting point. She's just slowing down. So now we switch to concave down. So for 0 to 5, f prime is positive. Okay, remember we can figure that out by drawing little tangent lines. Draw little tangent lines. Those all have positive slopes. And those slopes are getting more and more steep, which means that f prime is increasing. Okay, and then at t equals 5, my slope is positive. Okay, and then from 5 to 10, the slopes remain positive, but now they are getting less and less steep, which means values are decreasing. And f double prime on 0 to 5, because it is concave up, f double prime is positive. And from 5 to 10, the graph is concave down, which means f double prime is negative. And when a number changes from positive to negative, it would have to go through 0. So the f double prime right at 5 is 0, because f double prime is going to be changing from positive to negative at that moment, which means it must be 0. Okay, so from 0 to 5, Mandy moves forward while slowing down. We know that that looks like increasing concave down. Okay, moving forward means she's getting further and further away from her starting point. So if I label this distance, right, she's getting further and further away from um, 0, but she's slowing down, which means concave down. So we're concave down, increasing concave down until 5. At t equals 5, she momentarily comes to a stop. And then from 5 to 10, Mandy returns to her starting position while speeding up. So if she's returning to her starting position, her distance from her starting position is coming back to 0. So this is going to come back down to 0. And the question is it going to be concave down or concave up? So she is speeding up, which means the slopes should be getting steeper and steeper, which means I want to draw this concave down like that. So, because that is not very steep, a little steeper, a little steeper. And the steepness of the line tells you how fast she's moving. The fact that she's moving backwards is why those slopes are negative. So a steeper negative actually means faster. All right, so we've drawn the picture of it. Let's answer the question. So f prime from 0 to 5. So if I draw some tangent lines between 0 and 5, those lines have positive slope, but they are getting less and less steep. So the value of the slopes is decreasing. At t equals 5, the slope is horizontal. The line is horizontal, which means its slope is 0. F prime is 0. And then from 5 to 10, my slopes are negative. Okay, and what is happening to their values? It's starting at 0, and then it becomes a little negative, more negative, which means they are decreasing. And then f double prime tells us we can interpret from concavity. So from 0 to 5, this graph is concave down, which means that f double prime is negative. And from 5 to 10, the graph is still concave down, which means that f double prime is negative. At t equals 5, what is the concavity of the graph? At t equals 5, that graph looks like a frown. So it has f double prime would have to be negative as well, because the graph is concave down there. Okay, so putting it all together, curve sketching. Some useful terminology. A function is even if it is symmetric about the y-axis. So some examples of even graphs would be like that, y equals x squared, or y equals cosine x, which is a trig function like that, or y equals absolute value of x. And a function is odd if it's symmetric about the origin. So examples might be x cubed that looks like this, or the sine of x, which looks like this. Okay, so we want to sketch a differentiable function with all of the following properties. So f of x is even, which means it has y-axis symmetry. So I'm just kind of taking notes on what each of these things are. F of 0 equals 2. That means the point 0, comma 2 is on the graph. And f prime is positive for 0 to 2, for x's between 0 and 2. So f prime positive, that means that f is increasing on the interval 0 to 2. And then f prime is negative for x is bigger than 2. So that means that f is decreasing um, from 2 to infinity. F double prime is negative for x is bigger than 1. So second derivative negative means that f is concave down from 1 to infinity. And then f double prime positive between -1 and 1. So that means that f is concave up from -1 to 1. Okay, so now I just want to draw a graph that has all these properties. I'll do it on the next slide. Okay, let's start with the most concrete piece of information we're given, and that is the point on the graph 0, comma 2. So I'm going to go ahead and plot that. Now I really only have to plot um, either positive x values or negative x values because the graph is even. So if I know what one side looks like, the other side is the mirror image. So really, I'm just looking at positive. I'm going to look at positive x values, and I want to mark where the function is increasing and decreasing and where it's concave up and concave down. So f is increasing from 0 to 2. So I'm just going to mark up with some notes down at the bottom here. So 0 to 2, f is increasing. So I'm just making some notes here. And then f is decreasing from 2 to infinity. So f decreasing here. Okay, and then let's mark concavity. So f is concave down from 1 to infinity. So I'll do that in another color. So from 1 to infinity, f is concave down. And then before that, from -1 to 1, f is concave up. So I'll mark over here, even though I don't need to. Concave up. And now I'm going to try to draw the graph. Start at the point 0, 2, and I'm going to try to draw a graph that does these things. Okay, so from 0 to 1, my graph needs to be both increasing and concave up. So increasing, concave up until I hit 1. Okay, and then from 1 to 2, my graph continues increasing, but it becomes concave down. So until I hit 2, still increasing, but concave down. Okay, and then at 2, um, my graph continues to be concave down, but now it's decreasing. So from 2 until forever, the graph is going to be concave down and decreasing. So something like this. All right, and then I just need to draw the mirror image on the other side. So that, and then like that, and then like that. Okay, similar problem where we're going to sketch a graph that meets a bunch of given criteria. So f is continuous everywhere except at x equals 2. It's not differentiable at ±2 or at 4. And the graph of f has a vertical tangent line at x equals -2, but nowhere else. Okay, so the only ways a graph can fail to be differentiable are if it has a discontinuity, which we know it has at 2, but that's the only discontinuity, okay? And then a corner or a vertical tangent line, okay? So we have a vertical tangent line at -2, but nowhere else, which means that 4 can't be a discontinuity because we only have one of those at 2. It can't be a vertical tangent line because we only have one of those at -2. And the only other way you can fail to be differentiable is if you have a corner point. So at x=4, we must have a corner. All right, so now I just need to try to draw a sketch of this. So at 2, I have a discontinuity, and at -2, I have a vertical tangent line. So let's draw my vertical tangent line at -2. So maybe something like that. And then the next interesting point has to happen at 2. I need a discontinuity. So let's follow that to 2, and maybe I'll put a hole in the graph with a point up here. And then at 4, I need to have a corner point. So I'm going to continue this until I get to 4, and then I'm going to do a sharp corner like that. So I have satisfied all of the criteria here. Vertical tangent line at -2, a discontinuity at 2, and not differentiable at 4, but not because of a discontinuity or a vertical tangent line, because I'm only supposed to have one of those. All right, this brings us to our second activity for lesson 2.6. Please pause the video and work through this activity on your own, and then come back and finish this video. Okay, number 1, sketch the graph of a function on the interval -2 to 2 with the following properties. Label any points on the x-axis or y-axis which are important. Let's start by drawing notes at the bottom of the graph like we did in the previous example. Where I'm going to mark where f is increasing and decreasing and concave up and concave down. So the derivative and the second derivative tell me those things. So when they tell me that f prime is negative for x is less than -1, what they're really telling me is that f is decreasing for x is less than -1. So let's put a little note here and a little mark there, f decreasing for x is less than -1. Okay, and then f prime is positive for x's between -1 and 1. That means that f is increasing on that interval. Okay. And then f prime is positive for x's bigger than 1, which means f prime, which means that f is increasing. So f increasing for x is bigger than 1. Okay, I skipped over a couple of little pieces of information. We'll come back to those in a minute. I'm just trying to take notes on the increasing, decreasing, and concavity behavior. So now I'm going to look at anything that they tell me about f double prime to note concavity. So when f double prime is positive, they're telling me that f is concave up. So for x is less than 0, f is concave up. So less than 0, we have f concave up. And then f double prime is less than or equal to 0 for x's between 0 and 1. So less than 0, again, is concave down. So between 0 and 1, the graph is concave down. And then f double prime is positive again for x is bigger than 1. So we are concave up for the rest of the time. Okay, so let's see if I can draw this. I am going to highlight the important places where stuff changes. Okay, so I'm gonna, let's see, I'll do green. Um, right here, all of this green area, for all of this, f is decreasing and concave up. Okay, and then things change and f is still concave up, but it is now increasing. And then things change again here, and f is still increasing but concave down. Okay, and then for the rest of the time, F is increasing concave up. So let's see if we can draw it. Um, we need to start where F prime of -1 is 0. So that's going to be a horizontal tangent line at -1. So let's just put a little horizontal line there. And I know that to the left of that, F is decreasing and concave up. So it looks something like that. Decreasing concave up. Okay, and then in this region, the graph is still concave up, but now it's increasing. So it's going to go up like that. And F prime of one, F double prime of 0 is 0. So, well, let's just see. So concave up and increasing. It's going to go up and increasing like that. Okay, and then in this region, we are still increasing, but concave down. All right, and then from 1 on, we are going to be concave up and increasing. So continue increasing, but switch to up like a cup. So it looks something like that. Okay, so these are sort of important points, um, -1, 0, and 1 at f prime of -1 equals 0. That means horizontal tangent line. And f prime of 1 is 0. That means we're supposed to have a horizontal tangent line here. I didn't quite make that clear. Let me redraw this bit so that I have a horizontal tangent line there. Now that looks more like a horizontal tangent line. And then f double prime of 0 is 0. That's because I switched concavity from up to down, which means f double prime went from positive to negative, so it had to be 0 in between. Number 2, sketch a graph of a function f of x from the interval -2 to 2 with the following properties and label any points on the x-axis or y-axis which are important. Okay, f is odd, which means it's going to have origin symmetry. F double prime is positive for all x's greater than 0. And f double prime being positive means that f is concave up. So I'm going to write f concave up all along here. And then f prime of 0 is negative. So that means that the derivative at 0 is negative. So the slope of the tangent line at 0 has to be negative. So maybe I'll just put like a negative little tangent line there. And f prime of 1 is 0, which means I need to have a horizontal tangent line. And f prime of 1, oh, I just did that one. And f of 2 is 0. So that is a point on the graph. F of 2 is 0. So maybe my graph looks something like this. And then it has to have origin symmetry, which means it has to have symmetry um, where if you fold over the y-axis and the x-axis, the graph looks the same. So it's going to do something like that to have that symmetry.